P. So this is what we were proving. So the first case is if Q is equal to Qn, which we have demonstrated. That was the first case. And then the more general situation that it's strictly between 0. Q is strictly between 0 and Qn. So let's start with that. So 0 strictly less than Q, strictly less than Qn. So in this case, we can write Q as mu So this is the case. So we know that this convergence, the denominator of this convergence, Qns, they form a strictly increasing sequence. Therefore, we can assume that Q lies between two such. So suppose Qn minus 1 is strictly less than Q less than Qn. So that's always going to happen. If Q is not equal to a denominator of a convergent, then it will lie between two, strictly with strict inequalities on both sides. Then we can write Q as mu Qn plus say this is nu Qn minus 1. So mu and nu are non-zero real numbers. They are not a priori integers, but we would prove that they are integers. So see that. So we can always write a real number between two other real number in this form. And let P is equal to, P is defined in this way. So Q is what we get in this. So we get mu and nu from Q, and then use the same thing to define this P. So Pn plus nu Pn minus 1. Now just consider these as two linear equations in I forgot to disable. One second. Okay, so no accidental annotation. There were some, I guess there were some chat messages. Just let me check if there are questions. Oh no, distributing. Okay, so P we defined it in this way. So now consider these two as linear equations in mu and nu. So first step is to eliminate this nu, say suppose nu. Let's write them as 1 and 2. I think we have used 1 and 2 too many times. So, but I'll probably change the numbering when I send the notes. So eliminate nu. So if you do that, then you would get mu to be, let me write it. p into q minus 1. So we are eliminating nu. So multiplying the first equation, so p by this by q minus 1, second equation. This is the second equation. Second equation is multiplied by q minus 1 and first equation is multiplied by p minus 1. And then subtract. So we would get q p n minus 1. This is equal to mu times the same thing, p n q n minus 1 minus p n q n minus 1. But we know what this thing in the bracket is. So this is just plus minus 1. So this is just plus minus 1. So this is mu into minus 1 to the n minus 1 actually. So this is just plus minus 1. You can just roughly write it as plus minus p q n minus 1 minus q p minus 1. So one thing is clear, that mu is an integer. And similarly, once you know mu, we would know nu from the equations. So that is going to be plus minus pqn minus qpn. So these are non-zero integers. So they have to be non-zero because p by q is not equal to any other convergence. Now, an observation. Q is less than Qn, that is, and we have written Q as mu Qn plus mu Qn minus 1. So that is less than Qn. Therefore, mu and nu both cannot have the same sign. They cannot add up. So they have to have opposite signs. Therefore, mu and nu opposite signs. And that observation leads to another interesting observation. So if you write Pn minus Pqn x and nu of Pn minus 1 Qn minus 1 x, then these two quantities have same sign, because one of them is positive and the other one is negative. So they have opposite sign. The part in the bracket have opposite sign, and therefore if we multiply by this mu and nu, which have opposite sign, they have to have the same sign. So they have the same sign. These two have the either both negative or both positive. Same sign. Not some sign, same sign. Same sign. Yeah, so this follows from the fact that x minus Pn by Qn is equal to minus 1 to the n Qn minus 1. So convergence, the distance between x and the convergence change sign alternatively. So using this observation, the last one, what we can do now is write P minus Qx is equal to, so P is defined to be mu times Pn plus mu times Pn minus 1. If we use that, we would get mu Pn minus Qnx plus mu times Pn minus 1 minus Qn minus 1x. So both these quantities on the right side, both these summands on the right side have the same sign. Therefore, if I put absolute value, so then this is greater than P n minus 1. So these two have the same sign. So once you put absolute value, they would just add up. So therefore, this Pn minus 1 is greater than Qn minus 1x. As these are integers, so nu and mu are integers, and this is also greater than, so it's greater than both. It's also greater than both, so it's just greater than both. And P minus, so it has to be greater than both in absolute value. Yeah, so that proves the point. Okay, so there is a last piece of theory which I should just say about this approximation, the theme we are continuing. So this is essentially the last theorem. So of any two consecutive convergence, so if you take any two consecutive convergence, 2x, and of any two, at least one satisfy. So at least one comes very close. So what do I mean by that? That x minus p by q is 1 over 2q square. So at least one is this close. So to explain what I meant is the following. For any n, greater than equal to 1, either let's write it like this. Either x minus Pn minus 1 by Qn minus 1, the n minus 1th convergent is less than 1 over 2Qn minus 1, sorry, there is a 2 here, so 2Qn minus 1 square, or so one of these must hold. This is what the theorem is saying. 2Qn square. So Pn by either Pn by Qn or Pn minus 1 by Qn minus 1 must satisfy the equation we wrote in the theorem. So either of this inequality is true. So let's prove this. It's pretty quick. So we already know that every convergence satisfies this 1 over Q square, but without the 2. So we are saying a little more. So the same inequality without the 2 in the denominator on the right hand side is always true, but we are putting an extra 2 and saying that any two consecutive convergence one must satisfy this. Let's try to prove that. Proof. Okay. So let's just visualize this situation. So if we take two convergence, then what happens? So if we just draw a line. Oh, maybe shorter because we need to draw two such lines. So two situations might happen. So we might, so suppose we have x here. So it might be that n minus 1, Pn minus the nth convergent is here, and n minus 1th convergent is less than x and nth convergent is more than x. That might happen. Or the other situation also might happen, that the nth convergence. So we know that it depends on whether n is even or odd. Pn minus 1 by Qn minus 1. So it might be either of these cases. But whatever be the situation, we can write the following, that Pn plus n by Qn minus Pn minus 1 by Qn minus 1 in absolute value is equal to, so x is always between them. So we can, so the distance between these two convergence is equal to the distance, the sum of the, sorry, minus x, so sum of the distances between the convergence and x. Pn minus 1, Qn minus 1 minus x. That will always happen. So I just let me write. So better to just visualize it pictorially. So either this or this might happens. So therefore, this is always the case. Yeah, the last one is not a bracket, absolute value. So one of the two things might happen. So suppose what we wanted do not hold for either of these convergence. So suppose that so Pn minus 1 by Qn minus 1 minus x is greater than or equal to 1 over 2 Qn minus 1 squared. And so the what we wanted in the theorem is not satisfied by both the convergence, the nth as well as the n minus 1th convergence. Therefore, we are reversing the inequalities. So both has this. So this is and. So both happens together simultaneously. Now let's plug this information into the equality we have in the first line. So Pn by Qn minus Pn minus 1 by Qn minus 1 in absolute value is greater than equal to 1 over 2Qn square plus 1 over 2Qn minus 1 square. And let's work with the left hand side. So this is Qn minus 1, Pn Qn minus 1 minus Pn minus 1 Qn is greater than equal to 1 over 2Qn square plus 1 over 2Qn minus 1 square. Now we use just recall the equality we always use, that Pn Qn minus 1 minus Pn minus 1 Qn. This is just plus minus 1. So this is minus 1, I guess. Yeah, into the n minus 1 percent. Yeah. So in absolute value, the numerator of the left hand side is just 1. So we can write that 1 over Qn minus 1 is greater than equal to 1 over 2Qn square plus 1 over 2Qn minus 1 square. Let's simplify further. So therefore, what do we get? So if we let's just multiply like this. So okay, let's just do it here. So this is 2Qn square plus 2Qn minus 1 square by 4. Sorry, 2. This is Qn square, Qn minus 1. Yeah, this is what we get. Now, what does this give? So this is Qn square plus Qn minus square. I'm just changing side. So this is less than equal to 2Qn minus 1, right? So Qn minus Qn minus 1 whole square, if you just bring this 2Qn to this side, is less than equal to 0. Therefore, Qn is equal to Qn minus 1. So that's a contradiction, because it's a square less than equal to 0, so it has to be exactly 0. and then that's a contradiction. That cannot happen. So it is a contradiction. Yeah, actually for n equal to 0 case, it might happen, but then you can show it in directly that that's not the case. So, okay. So what we have proved is, so that's a contradiction. Let's write that. So that is a contradiction. Which establishes the theorem. So what's the theorem we proved? We showed that among any two consecutive convergences, if you take two consecutive convergence, so one of them have to satisfy this inequality, that 1 minus p by q is strictly less than 1 over twice of q square. So that is, this inequality is satisfied by one of the convergence. So one of the convergence gives you an approximation of that accuracy. Okay. Actually, the converse is also true, that if this inequality is satisfied, then p by q has to be a convergence. So converse is true. I won't prove it now. So converse, let me just write that. If x minus p by q, so if a rational provides an approximation of that precision, 1 over square root of q, so 1 over q, 1 over 2 twice of q square, then p by q is a convergent. So I'm going to skip the proof. So proof. So please see Hardy right. This is the last theorem of that chapter. The chapter in Hardy right. Okay. So with that, we are done with the theory we wanted to do. Now, as I was saying yesterday, we will talk about pi. So pi is, of course, something difficult to approximate. Though from our school days, we are using the approximation to 22 by 7 all the time. And approximating pi was an important problem and was considered by all ancient civilizations. So there is very interesting history, and there were a book about this. So there is a book called History of Pi. So it gives all the details with original manuscripts in many cases. Okay. So, but we won't talk about history. We would go to a. We'll start with a formula. Start with an interesting formula. So let me just go to a new page. It's a bit different. Yeah, though our goal is to look at the continued fractional expansion, we have to talk about the decimal expansion of pi as well. So we would talk about pi now, and the first thing what I wanted to do is a theorem. So interestingly, it's proved by Madhava. So it's called Madhava-Leibniz theorem. So Madhava and Leibniz. So it's a very beautiful expression for pi. It says pi by 4 is 1 minus 1 over 3 plus 1 over 5 plus, sorry, minus 1 over 7. So reciprocals of odd numbers appearing alternatively. Reciprocals of odd number with alternate sign. So an infinite series. So that's the theorem. The proof is very easy. Proof is very easy. Probably not at the time of Madhava. At the time of Madhava, it was probably very difficult, which is 14th century. So Madhava is from 14th century. And the proof was rediscovered by, of course, they did not collaborate together. They differ by a few hundred years. So Leibniz rediscovered the proof in 1676. For us, the proof would be very easy. So let's prove it. Yeah, because we know a lot more. So the proof is using very elementary calculus. So we know this infinite series that one might. Okay, so let's put the restriction. So for a real number in between 0 and 1 in absolute value, we write the infinite series 1 by 1 minus what we write this quotient as an infinite series 1 plus y plus y squared plus y cubed, etc. Now just let's modify this bit. So put y equal to minus x squared. And then what we have is 1 plus x squared is equal to 1 plus x squared plus x to the 4 plus x to the 6 plus x to the 8 and goes on. Oh, sorry, the sign alternates. Sorry, this is wrong. So sign alternates because we are using minus x squared. So sign is going to alternate. So this is minus, this is plus, then minus. All the odd powers are going to be minus. All the odd powers of x squared. Now integrate with respect to x. So integrate. Of course, we are taking a bit some things for granted. For example, integrating an infinite series term by term. But let's suppose I mean those can be proved rigorously that it can be done in this case. So integrate integrate both sides. Obviously with respect to x. So what we get is tan inverse of x, which is also called arctan. So tan inverse of x is x minus 1/3 x cubed plus 1/5 x 5 minus 1/7 x 7 plus 1/9 x to the 9, etc., etc. Now just put x equal to 1. So tan inverse of 1 is pi by 4. So pi by 4 is 1 minus 1/3 plus 1/5 on 9. There is one little problem here. So we have established this formula for y strictly less than 1 in absolute value. So x also have to be strictly less than 1. And then we are using it for exactly for 1. So there is a slight bit of a slight bit of a thing to justify. Just assume for the moment that it can be done. We won't get into the analysis now. So suppose that can be done. It's clear that the series on the right hand side, this alternating series of reciprocals of odd number is convergent. So there is not much of an issue. Can be done. So this is a proof. It's a simple proof, just hiding a few details. But even though this formula is very nice, if we try to approximate pi using this formula, we would see that it's not good enough. It's not good enough. The convergence, it of course going to converge to pi, meaning if you multiply the right hand side by 4, so 4 times that series, it's going to converge to pi, but the convergence is very, very slow. I actually computed a few, so just whatever I could with my calculator. 1 second, I want to just show you that. If I can just manage to get that. Yeah. It's too big. Okay, 1 second. Just make it smaller. Yeah. Okay. Yeah. Yeah, it's a bit small. May not be able to see it fully. So I just used this Maple calculator on my phone to do it. So I have taken 30 terms, so till 61, so 30 terms. And what we get is this rational number, but if you look at the approximation I got, so if you look at the approximation I got, then you would realize that it's correct only up to the first decimal digit. Only up, it only got this first digit, which is 3.1, that is right. Because we know that its pi is 3.14159, etc., etc. So that's it just got just 1 digit correct after taking this many 30 terms. So it's very, very slow. So then what is a good thing for approximating pi? So there have been many attempts and many formulas to do that. I will just talk about some. Okay. So one of the most powerful formula is by Ramanujan that he proved in 1911, so just 100 years back. So this is that's the first thing. So, but that's the one of the fastest converging series for pi. It's written for 1 over pi, but once you know how to approximate 1 over pi, you would also know how to approximate pi. So 1 over pi. So this is Ramanujan. So this is essentially the best known series. There is a modification by 2 Russian mathematicians, but that's also quite in the same line. And this formula is still used to approximate. So there were algorithms which use this series. So people have calculated some billions of digits of pi using this kind of strong formulas. Let me write it down. So it's a bit cumbersome, as with many formulas by Ramanujan. So square root of 8 by 9809 4n factorial by this factorial by n factorial power 4 into a quotient 26309 390 n plus 1103 by 396 power 4 to the n, 4n, 4n, not 4 to the n, 4n. So as you can see, the convergence is extremely fast. The denominators, I mean, if you just take n equal to 1, you get a huge denominator. So the convergence is extremely fast. So I just tried the first term. So just n equal to 0. Just take n equal to 0. Then, so if you take n equal to 0, then you have 1, 1, 1, 1, 0, 3. So let me write this. So 1, 1, 0, 3 square root of 8 by 9809. So if I take that, then pi is, I'm trying to approximate this by the inverse of that. Inverse of just the first term. Even that provides quite a bit of things. So 1/4. So if you calculate, this is going to be 3.1415927 300 113, etc. So that's going to be the decimal expansion, and this is correct up to this much. Correct up to 5 decimal digit. So this is correct up to 5 decimal. Just the first term itself. So if you take few more terms, we are going to get many decimal digits. So very powerful formula. Of course, we won't see a proof of this. But let's try to calculate a few convergence of pi using this decimal expansion. So we are just going other way around. So let's try to calculate. So I have done that. I wanted to show it to you. So let's just take this. So let's call x equal to. So it's not exactly pi. So just giving it a name, that 3.14159. Let's just take this much. It's not exactly, it's not pi, but it's an approximation up to 5 decimal places. Oh, actually, I wrote something wrong. This is up to correct up to this. It's correct up to this. One would be that. So correct up to 2. So 6 decimal places. So let's take that. So then take this one, 2 and 7 as well. So let's consider this. Let's call this number x, and we would try to write the convergence. So this is the number. So x is equal to 3 plus 1 over x1. So obviously the integral part is 3, so it starts with 3. And what is x1? x1 is going to be 1 over x minus 3. And this is, this turns out to be, if we just subtract, yeah, so this is what, and okay, let's use the notation we are always using. So the first entry of the continued fraction expansion is just 3, and the second one, so if x1 is this, so x1 is the first complete quotient. So this is first complete quotient. First complete quotient. First complete quotient, and therefore, as we know that a1 is the integral part of. So this is what we were writing as a1 dash, actually, first complete quotient. So this is a1 dash. It's also written as a1 dash. Maybe I should write that. Let me write that. So then just have the same notation that we already have. So a1 dash. So this is a1 dash. So a1 dash is 1 by x minus a naught, actually. So a1 is the integral part of a1 dash, which turns out to be 7. So what we have at this stage, we have x equal to 3 plus 1 over 7 plus, say, 1 over a2 dash. So a1 dash is equal to now 7 plus, so 7 plus 1 over a2 dash. And a2 dash can be then calculated to be yeah, so yeah, sorry, a2 dash is you can write it, of course, as a1 dash minus 7, and a2 is now integral part of a2 dash which turns out to be 15. So these are just checked by calculator, just the usual calculator on mobile phone. So it's very easy. So 1, 5, so 15. Then the next one. So just continuing this. So A3 dash is equal to 1 over A2 dash minus 15, A2 dash minus A2. So, and this is going to be 1 point something, etc. And we get, so if we just calculate, so A3 is the integral part of A3 dash, which gives you 1. And 2 more, let's do 2 more. So this is A4 dash is 1 by A3 dash minus A3, so that is 1. And A4 is going to be A4 is going to be, yeah, that's very interesting actually, 354. 354, such a large one, certainly. A5 dash is 1 over. So just to see whether this kind of large things remain. So A4 dash minus 354 and A5 is equal to the integral part of A5 dash, which turns out to be just 2. Yeah, it is just 2. So calculating this much is fairly easy. So what we got now, so what are the integers which are appearing in the continued fraction expansion? So it starts with 3, then second one is 7, then A2 is 15, 16. Sorry, this is A3 is 1, then 354, and it goes on. So what we got is the following. So what was our x? 3.1415927. This is what we started with. 1415927, 1415927, and we saw that this has an expansion of this type. So 3, then 7, I guess 1, and 3, 7. So 3, 7, 15. Sorry, 3, 7, 15, 1. 1, 354, comma 2, and it goes on. Of course, so the number we are considering is a rational number. We have terminated the decimal expansion of pi at the 6th decimal. So what we have on the left hand side is a rational number. Therefore, the continued fraction expansion is going to be finite. It's going to terminate. But just let's look at the first few convergence. First few convergence. And let's look at the first convergence. So P naught by Q naught. So P naught by Q naught is simply 3. And P1 by Q1 is 3 plus 1 over 7. So this is the one we always use, 22 by 7. That's the so that's the next convergent. And then what do we have? Yeah, so notice one important thing. So since you have a very large, so this is very large. So we have noticed this earlier in the context of calculated something where we had this same situation. I can't recall that which one. So anyway, so if you have a very large partial quotient, then you can just terminate before that, which would give you a very good approximation. Because the next one is going to be too small. The contribution coming from the next one is going to be small. That's the reason. So let's calculate the next two. So P2. So P2 by Q2 is 3 plus 1 over 7 plus 1 over 15. So this is what I have already calculated. So what you get is 333 by 106. 333 by 106. P3 by Q3. So if you calculate the next one, it's going to be 355 by 113. This is actually a very good approximation. This is a very good approximation to pi. Yeah. So we actually did not calculate with pi. We calculated with a decimal approximation to pi. So the whatever we called x, so this here on the right hand side is not exactly pi. It itself is a rational approximation. So the continued fraction expansion what we got won't exactly match the continued fraction expansion of pi. So let me just write that so we can compare. So CF continued fraction for pi is the following. So 3, 7, 15. Then we have, as we have 1. And then we have a large entry, but this is 292 instead of 354 that we got. So we, of course, we would be getting things wrong because we are not actually approximating pi, but approximating a decimal approximation. So 1, 1, 1, 1, 2, 1, 3, 1, 14. Oh, just a second. I have to close my window. There is some noise. One second. Yeah, I guess slightly better. Yeah. So that's the continued fraction expansion for pi. So what we got is good up to this three entries, four entries. So we got 3, 5, 1. Yes. Sorry, if it's a question, please repeat.
No question, sir.
Oh. So that's, but there were some more interesting things with pi. So I'm just thinking which one to talk about. Okay, let's do something else about pi. Yeah. Yeah, so there is one important question is to find pattern in this continued fraction expansion of pi. So it seems that there are no pattern. So that's kind of an open problem to determine pattern in this continued fraction expansion. It seems very random. So there were some work in this. But as we saw that there is some interesting pattern in the series we started with, that Madhava-Leibniz series. It has very interesting pattern. It consists of the reciprocals of odd numbers with alternate signs. So we can play with this to find an interesting continued fraction, though it is not a continued fraction of the kind we are working with. I would explain as I do that. Let me just go to add a page. So a continued fraction for pi so it's a different kind of continued fraction. I would write it so that you see this thing. So pi by 4 can also be written as 1 over, let me just write this carefully. 1 plus 1 by 2 plus 3 square. So we are allowing integers in denominator which are not necessarily 1. So here, so far we are considering continued fraction where all these are 1. So these numerators are always 1. So we are, so this is not the case here. So when we talk about this continued fraction expansion of pi, it is of that form. Which is right. So this is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292, then plus 1 over 1 plus 1 over, exactly. So it just goes on like this. So it is always 1 in the numerators. So all these consecutive numerators are going to have 1. But if we allow different type of continued fraction, then we would get this very interesting formula. Pi, this is 3 square by 2 plus 5 square by 2 plus 7 square by 2 plus 9 square by 2 plus, it goes on like this. So very interestingly, again, this odd numbers appears with squares, and you have this 1 followed by infinitely many 2. So that's a very interesting looking continued fraction. Such nice pattern. Actually, the proof of this is very simple. So let me just prove it. Let me just prove it, at least the first few terms. Then you can continue proving this with induction. Let's prove this. Let's see how to prove such a thing. So suppose you have two reals, alpha 2 is greater than alpha 1, then let's look at what is alpha 1. 1 over alpha 1, let's look at the difference between the reciprocals. So this is let me write it next. 1 over alpha 1 minus 1 over alpha 2. So this is a positive quantity. This is alpha 2 minus alpha 1 by alpha 1 alpha 2. Let's invert it. So this is alpha 2 alpha 1 alpha 2. Let's write alpha 1 alpha 2 by alpha 2 minus alpha 1. Now let us write this as 1 over alpha 1 alpha 2. Okay, so we are adding alpha 1 square and subtracting alpha 1 square from the from alpha 1 alpha 1 square, alpha 1 square. Just adding and subtracting the same thing, and the denominator is alpha 2 minus alpha 1. So 1 over, so what we have is alpha 1 square plus, then if you take alpha 1 common, alpha 2 minus alpha 1 divided by this alpha 2 minus alpha 1. So what we get is 1 over alpha 1 plus alpha 1 square by alpha 2 minus alpha 1. This is what you get. So we are going to use this. So let me write it as a direct formula. 1 over alpha 1 minus 1 over alpha 2 is equal to 1 over alpha 1 plus alpha 1 square by alpha 2 minus alpha 1. So we are going to use this repeatedly. So this is the formula we are going to use repeatedly. So let's see first few terms. So 1 minus 1/3. That's of course very easy. So alpha 1 is 1, alpha 2 is 3. Then this is 1 over alpha 1. So 1 plus 1 square by alpha 2 is 3 minus 1. So that is 2. Now 1 minus 1/3 plus 1/5. So we have to use the formula twice. So 1 minus 1/3 minus 1/5. So use the formula for the bracketed expression 1 minus 1 by so alpha 1, so 3 plus 3 square by the difference, which is 2, and then use it again. So if you use it again, then what you have is 1 by alpha 1 is now 1. So 1 plus uh, 1 by, yeah, okay, it won't, it's not, the space is not enough. So just go to the next page. Just copy paste this. Yeah. So I do the same, I use the same formula. So that is, that gives me 1 over 1 plus 1 by the difference. So this minus 2. So 2, this minus 1. So this alpha 2 is 3 plus 3 square by 2. So if I subtract minus 1, which is alpha 1, then I get a 2 plus 3 square by 2. And let's do the next one. 1 by 1 minus by 3 plus 1 by 5 minus 1 by 7. So this is 1 minus 1 third plus, we need to use the formula thrice. You can try proving the general formula using induction. So I'm just doing a few steps to show the pattern. And so this is 1 by, use the same formula. So 5 plus 5 square by 2, the difference. And then use it for 1 minus 1 third minus 1 over 5 plus 5 square by 2. One minus 1 over same formula. So alpha 1, which is 3 plus 3 square by the difference. So the difference is again 2 plus 5 square by 2. Use it once more. Use the same formula once more. 1 over alpha 1 is 1 by 1. And then if you subtract these two, the difference is 2 plus 3 square by 2 plus 5 square by 2. So if we continue by induction, continue by induction, and this is a very interesting equality to prove. It's very nice, continued fraction expansion. It shows a pattern. Okay, so my time is essentially up. So I just want to. So can I just take 3-4 minutes more?
Sure, sir.
Okay, thank you. So I just wanted to mention 2 questions actually to explore. One is a very interesting phenomena. Let me just write down a few things, you would see that. So we have seen some continued fraction expansion. So I'm talking about the quadratic irrational. So we know that they are continued fraction expansions at periodic. And so now what the, okay, let me add a page. So there were important questions regarding the period of those functions, the length of the the periodic part. So that's called the period. So that so there were very interesting questions about that. But now we see an interesting phenomena. Let's write down an example. So hopefully I'm writing the fraction, the expansion correctly. So square root of 5, I just calculated these things just before the lecture. So square root of 5 is 2, 4. 4 is the periodic part which repeats. So I'm writing with a bar on it. So 2, 4. Now, if we multiply this by 2, so let's just multiply by them, multiply the square root of 5 by whole numbers. Let's see what happens. So this is 4, 2, 8. This part repeats. Then let's write 3 square root of 5. So multiplying it by 3. Then the expansion is 6, 1, 2, 2, 2, 1, 12. And this part repeats. So it's such a long block suddenly. 1, 2, 2, 2, 1, 12. And so does this continue to have this kind of large blocks? The answer turns out to be no. And the next multiple, the 4 is 8, 1, 16. 16. So 1 and 16 repeats. Then 5, let me write that 5, this much I have calculated. So I use the online calculator to calculate this. It's very nice actually. So 11, 5. I think you should try this online calculator. It gives very nice, interesting things. You can experiment with these numbers. And 5, 1, 1, 5, 2 repeats. So we can clearly see that the length of the period is really varying. So here it is just 1, and if we multiply it by 2, we get 2. Then if I multiply it by 3, then we have 1, 2, 3, 4, 5, 6. And then it again comes back to 2. Then it again goes to 5. So there is no clear pattern, and it's actually an interesting problem to look at this. There are some literatures. So if you wish, you can explore. So 1 second. So why we are talking about the interesting pattern? Why anyone would look for pattern in continued fraction expansion of pi? So it's interesting, and also if you see the expansion of E, I wanted to actually do it, but I couldn't because so many things can't be done. So if you write E, the exponential in continued fraction expansion, I at least wanted to show the expansion. Let me just write that correctly. So this is 2, 1, 2, 1, 1. And then it is 4, 1, 1. Then this pattern continues. So it is 1, 1, 6, 1, 6, 1, 1, and this kind of thing continues. So it looks like 1, 1, 2, n, 1, 1. So it is certainly not periodic, because had it been periodic, then this E would be a quadratic irrational, which it is not. E square is not a rational number. That we know. We know that it's a transcendental number, in fact. So it's not periodic, but it has this pattern. So that's very interesting. I wanted to prove but couldn't. So anyway, so I would end with a formula by Ramanujan. So this is a question by Ramanujan, so to say. Question. So he posed this question in 1910 or 11. So this is a famous question of Ramanujan. And then nobody could answer, so he answered it after a few months. So the question is the following. So what is this repeating pattern? So that's the question. Some of you might have already seen that. So this is a nesting of square roots. So 1 plus 2 square root of, so it just goes like continued fraction, but it is not. So 1 plus 3 square root 1 plus 4. So all the numbers, so square root 1 plus 5 square root. It goes on like this. So infinite nesting of square roots and with this pattern. So he asked, what is this? So the question is, what is this number? So I won't give you the answer. So you can explore this question by Ramanujan. Of course, he himself answered it in 1911. So thank you for your attention, and sorry for taking 10 more minutes actually. So any questions? So I urge you to try this continued fraction calculator. It gives interesting thing, and also do this kind of experiments with these periods of quadratic rational. It's very interesting. You can in fact look at the list of periods of square root of n. N is a whole number. So just take keep taking the square root of whole numbers and look at their continued fraction expansion. They give very interesting periods. So I'll send the lecture notes by tomorrow and also send some references to this kind of things.
Okay, sir.
Thank you, sir. So good evening to all. On behalf of Department of Mathematics, Mukhopadhyay Engineering College, Sivakasi, I would like to thank Professor Anirban Mukhopadhyay, IMSc Chennai, for being a convener and for delivering the lecture on this online workshop on linear algebra and elementary number theory, sponsored by NASI and CMI. We all agreed that your lecture on number theory was the most interesting to hear, and it refreshed our brain to gain knowledge, and we are aware of some online calculators also. Thank you. Your flow of lecture is excellent, and we thank you for sharing your time and experiences with us. I expect that your journey together with us and MEPCO will continue in future. Thanks again for your support and guidance for convening this workshop. Thank you, Anirban sir. Thank you.
Thank you.
Okay, sir.
Thank you, sir. Thank you, sir.
Thank you.
Thank you so much, sir.
Yeah, see you next time.
Okay, sir. So we request you to join in the coming Sunday valedictory function around the 6th.
Surely. 27th I'll be there. Yeah.
Okay, sir.
Okay.
Okay.
See you
Thank
on
you,
27th.
sir.
Yeah.
Okay.
Bye.
Thank you, sir. Bye.